Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, becomes our gentle guide through starships, wormholes, quantum foam, and the strange question of whether space itself could ever become a road. For now, imagine a starship holding position near the edge of a silent anomaly. The bridge lights are low. The stars on the view screen are steady, but they do not look quite right. They bend near the center of the image, as if the sky has been gathered inward by invisible hands. Long-range sensors show no planet, no moon, no ordinary nebula, no familiar cloud of gas and dust. There is only a region where distance has become uncertain, a place where the map refuses to behave like a map. The captain does not give the order to enter. Not yet. First, the science officer studies the readings. The helm waits. Engineering watches the structural stress along the hull. Communications listens for a signal from the far side, though there should not be a far side at all. A starship is built for motion, but at moments like this, the wisest thing a ship can do is pause. Because a doorway in space is not like an ordinary doorway. An ordinary doorway tells you what it is. It has a frame, it has hinges, it opens into a room. But a doorway in space-time is a deeper promise and a deeper risk. It says that two places, perhaps thousands or tens of thousands of light years apart, may be close in a way that ordinary distance cannot explain. It says that the galaxy may have a hidden fold. It says that a ship may not have to cross every mile of darkness to arrive. If you were watching from Earth, that promise would feel almost impossible. Sunlight itself takes about 8 minutes to reach home. Light from the nearest star system takes more than 4 years to arrive. Light from Andromeda begins its journey millions of years before it touches a human eye. Even light, the fastest messenger nature allows, turns the sky into a memory. A wormhole, if one could be crossed, would not merely be a faster engine. It would be a challenge to the way distance, time, and memory fit together. This is one of the great dreams of science fiction. The starship before the impossible shortcut. The vessel with its lights glowing softly in the dark, waiting at the mouth of a passage that should not exist. In Star Trek, the most famous version of that dream appears near Bajor, where a stable wormhole connects the Alpha Quadrant with the distant Gamma Quadrant. To Starfleet, it is a navigational discovery. To the Bajorans, it is the Celestial Temple, home of beings they call the Prophets. To merchants, diplomats, explorers, soldiers, refugees, and empires, it is something else again, a new geography. That is the first wonder of a wormhole. It does not merely shorten a trip, it changes what a place means. Before the Bajoran wormhole is discovered, Deep Space Nine is a worn, damaged station near a wounded world, left behind after occupation and conflict. After the wormhole opens, that same station becomes a threshold. Ships arrive that would never have come before. Maps are redrawn. Trade routes shift. Alliances tremble. The unknown side of the galaxy is suddenly not a remote abstraction, but a place with an address. The wormhole turns distance into politics, science into pilgrimage, and exploration into responsibility. That is why the Bajoran wormhole is such a powerful doorway for tonight's journey. It gives us the perfect fictional version of a cosmic shortcut. Stable, large, navigable, reusable. Close enough to a settled system that starships can line up and pass through. A luminous corridor in the dark, generous enough to behave almost like a canal through the galaxy. But tonight, we are going to ask a more careful question. Not simply, could a starship fly through a wormhole, but what kind of universe would have to exist for space itself to become a road? And as we follow that question, we will move across three very different scales. First, the grand scale of fiction, where a starship can enter a glowing passage and emerge almost instantly in another quadrant. Then the mathematical scale of general relativity, where Einstein and Rosen found a bridge hidden in the equations, beautiful and strange, but not built for travel. And finally, the smallest scale of all, where physicists wonder whether space-time may become foamy, restless, and uncertain, not as a tunnel for ships, but as a possible texture of reality itself. The journey begins with a starship before a doorway, but it will end far below the ship, far below its hull, far below its atoms, in a realm so small that the word crossing no longer means what it means on a map. Let us begin with the part a new viewer needs to know, gently, without rushing. A wormhole is a hypothetical shortcut through space-time. In the simplest picture, two distant regions of the universe are connected by a passage that is shorter than the ordinary route between them. The usual image is a sheet of paper with two dots drawn far apart. If you travel across the surface, the journey is long. If the paper could fold, bringing the two dots close together, a tunnel between them would be a shortcut. That image is useful, but it is also limited. Space is not literally a sheet of paper. Space-time is not a flat surface waiting for a pencil to pierce it. The real theory is general relativity, Einstein's description of gravity, where mass and energy shape the geometry of space-time, and objects follow the straightest available paths through that curved geometry. In that theory, what we call gravity is not just a force pulling through empty space. It is the shape of space and time themselves. This is why the wormhole idea is so tempting. If space-time can curve, perhaps it can curve in more complicated ways. If massive objects can bend the paths of planets and light, perhaps under extreme conditions, the geometry could connect regions that look distant from the outside, but are joined through some deeper interior. The key word is perhaps. No confirmed wormhole has ever been observed. No telescope has found one. No probe has entered one. No star has been seen vanishing into a stable cosmic passage and reappearing elsewhere. General relativity permits bridge-like mathematical structures, but mathematical permission is not the same as physical existence. The universe can allow an equation to be written without promising to build the object the equation describes. For a starship, this distinction matters. A ship does not need a poetic possibility. A ship needs conditions, a mouth it can approach, a throat that stays open. Tidal forces mild enough that the ship is not stretched apart. Radiation low enough that the crew and systems survive. A route that remains connected to the destination long enough to cross. A way to communicate through or around the passage. A guarantee, or at least a hope, that entering the shortcut does not mean becoming trapped inside a horizon, crushed by a geometry, or sent into a different time in a way that breaks cause and effect. So when a starship approaches a wormhole, the first question is not romance, it is stability. Is the doorway still a doorway when you reach it? The Bajoran wormhole answers yes, because fiction is allowed to be generous. Its near mouth opens in the Bajoran system. Its far mouth leads to the Gamma Quadrant. Starships can pass through and return. The passage is not merely a one-time accident or a trembling anomaly. It is reliable enough to become a center of civilization. That reliability is the miracle. In many Star Trek stories, wormholes are uncertain. Some are unstable. Some are too small for a ship. Some lead to the wrong place. Some lead to the wrong time. Some are valuable only until careful measurement reveals the danger hidden inside them. This is closer to the real scientific problem. A shortcut that opens for a moment and collapses before anything can enter is not a route. A passage whose exit wanders unpredictably is not a safe road. A throat that destroys the ship is not an answer to interstellar distance. The Bajoran wormhole works because it removes almost every operational problem at once. It is large enough, it is stable enough, it has known ends. It allows repeated travel. It does not require each ship to carry a universe-bending machine in its engine room. It simply exists, waiting like a door in the dark. And because it exists, ships behave differently around it. Imagine a cargo vessel approaching from Bajor, its hold filled with supplies for an outpost that would once have been impossibly remote. Imagine a science ship emerging from the Gamma Quadrant with sensor logs full of stars no Federation telescope has studied up close. Imagine a diplomatic courier, a defense patrol, a refugee transport, a runabout carrying one officer and one urgent message. Each vessel is small compared with the galaxy, but the wormhole gives each vessel a new kind of reach. Picture the Defiant holding close to the station, compact and armored, not built as a graceful explorer, but as a vessel made for hard choices near a dangerous frontier. Picture a runabout slipping ahead of larger traffic, small enough to feel fragile against the opening, its crew watching the instrument panel as the stars seem to rearrange themselves. Even the Enterprise or Voyager, ships made famous by distance, would have to treat such a passage with respect. A wormhole does not care how legendary a name is painted on the hull. The ship does not conquer distance. It negotiates with geometry. Real physics is less generous. To understand why, we have to leave the station window for a moment and return to a quieter scene. A set of equations, a blackboard, and the year 1935. Albert Einstein and Einstein-Rosen were not writing a starship adventure. They were working inside general relativity, trying to understand whether particles and fields might be represented without singularities, those troubling places where the mathematics seems to break down. In their work, they described a structure that could be understood as two identical sheets of physical space connected by a bridge. That bridge became one ancestor of the modern wormhole idea. But it was not a practical tunnel. It was not a glowing road to another star. It was not the Bajoran passage waiting for ships. It was a mathematical structure, a clue in the geometry, a way the equations could be read under idealized conditions. There is a quiet humility in this. Science fiction often begins with the door already open. Physics begins by asking what kind of door the equations are even describing. The original Einstein-Rosen bridge is sometimes imagined as a passage between two regions of space-time, but it is not the kind of passage a crew could simply enter. In the familiar black hole-related version, the bridge pinches off too quickly. It does not remain open long enough for even light to travel through from one side to the other. In practical terms, the starship arrives too late, no matter how early it arrives. The geometry is already closed. This is the difference between a bridge and a road. A bridge in mathematics can reveal that two regions are connected in the structure of a solution. A road in engineering has to remain usable. It must carry weight. It must endure weather. It must allow travelers to cross before it collapses. A starship corridor through space-time would need the same kind of reliability, translated into the language of gravity. It would need a throat. The throat is the narrow interior region of a wormhole, the part that must remain open if anything is to cross. Ordinary gravity tends to pull inward. Ordinary matter and energy curve space-time in ways that do not naturally hold such a throat open. In many models of traversable wormholes, something more exotic is required: negative energy density, or matter that violates the usual energy conditions. Exotic matter can sound like a fuel in a science fiction cargo bay, but in real physics, it is more like a warning sign. It tells us that the model needs something unlike the ordinary matter we know how to gather, store, or build with. It does not mean there is a mineral waiting in an asteroid field, ready to be loaded into the ship. It means the mathematics is asking for a kind of stress and energy behavior that may not be available in the universe at useful scales. Small negative energy effects can appear in quantum field theory under special conditions, but that is not the same as a starship-ready supply of throat-supporting material. A tiny laboratory effect is not a galactic bridge. The difference in scale is enormous, and the difference in control is deeper still. So the starship waits. It waits before the mouth of the possible wormhole, and the crew asks the questions that matter. How strong are the tidal forces? Tidal forces are differences in gravity from one part of an object to another. Near an extreme gravitational region, the front of a ship may feel a different pull than the back. The hull may be stretched, the frame may twist, the crew may feel nothing at first, or the ship may groan before the sensors finish explaining why. A traversable wormhole would have to be shaped so those differences remain survivable. What happens to light? Around strong gravity, light bends. Real astronomers use gravitational lensing to see distant galaxies magnified and distorted by mass between us and them. Near a wormhole, if one existed, light might behave in unusual ways. A starship might see repeated images of stars, rings of distorted background light, or a view through the far mouth mixed with the sky around the near one. The view screen might become less like a window and more like a question. Can the ship communicate? A route is more than passage for bodies. It is passage for information. Can a signal cross the throat? Does it arrive before the ship? Does it return? Does the wormhole create delays, echoes, distortions, or impossible loops? A captain may be brave, but even bravery prefers a channel home. Does the shortcut disturb causality? This is one of the deepest problems. If two wormhole mouths can move differently through spacetime or experience time at different rates, a traversable wormhole can begin to resemble a time machine. A ship might not simply cross distance. It might cross cause and effect in a way that makes the universe uncomfortable. Physics has many ways of protecting order, or at least many suspected ways. But the question remains one of the reasons wormholes are studied so carefully. And finally, is the wormhole natural, artificial, or impossible? The Bajoran wormhole gives one fictional answer. It is stable because the story gives it a reason to be stable. It is not merely a physical object, but also a temple, an encounter with beings outside linear time. In that story, the root is not just geometry, it is relationship. Real physics cannot use that answer. Real physics has to ask what matter, what energy, what boundary conditions, what quantum effects, what cosmic history could make such a structure exist. And if those ingredients cannot be found, then the wormhole remains a beautiful possibility inside the mathematics, not a road on the star chart. Imagine the ship plotting the same question on a familiar scale first. A signal from Earth to the Moon is delayed only by a heartbeat. A message across the inner solar system can become a conversation stretched by minutes. A probe near Jupiter waits much longer for the answer from home. By the time the map reaches the nearest stars, even light has become slow enough to make ordinary travel feel almost dreamlike. This is why shortcuts are so tempting. They are not just shortcuts through space, they are shortcuts through waiting. From Mars' orbit, the same truth would feel personal. Earth would be a bright point in the black, close by the standards of stars, but still far enough away that a calm question and its answer could not feel instant. The crew would understand distance not as a number, but as a pause in the conversation. A simpler journey could have ended here, with the starship before the wormhole and the honest boundary drawn clearly around it. The dream is grand. The mathematics is real. The observed object is missing. The engineering is far beyond anything we know how to do. But tonight, we keep moving. Because there is another phrase near the edge of this subject, a phrase that sounds as if it might belong beside wormholes, but really belongs at a far smaller and stranger scale. Quantum foam. Before we descend to that scale, stay with the starship a little longer. Imagine the captain authorizing a probe. It leaves the shuttle bay like a small silver thought, crossing the dark ahead of the ship. It has no crew, no windows, no fear. It carries cameras, field sensors, radiation counters, clocks, transmitters, and a simple instruction: enter only if the mouth remains stable. On the main bridge, the crew watches telemetry fill the displays. The probe measures the shape of the opening. It checks whether the gravitational field changes smoothly or violently across its path. It sends out pulses of light and waits for the echoes. It looks for a far side signal. It compares its onboard clock with the ship's clock because in strong gravity, time itself can become part of the navigation problem. A human pilot thinks of steering as left, right, forward, back. A starship near a wormhole must think in geometry. The safest direction may not be the direction that looks straight on the view screen. The shortest path may not be the path that appears shortest on a map. Light may curve. Distance may change meaning. The ship's computer may need to calculate not only where the vessel is, but what the local shape of space-time is doing to the word where. This gives us a better way to understand why a stable fictional wormhole is so generous. The Bajoran wormhole does not merely open, it behaves. It allows ships to develop procedures. It allows a station to monitor traffic. It allows pilots to learn approach vectors. It permits schedules, warnings, patrols, commerce, and return journeys. Once a route can be trusted, it becomes part of ordinary life. The first crossing is a miracle. The 1,000th crossing is infrastructure. That is how deeply a stable shortcut would change civilization. An unstable wormhole would create a different kind of story. It might appear as a flicker on subspace sensors, a narrow tremor in the background, a throat too small for the ship but large enough for a message. It might let a crew speak to home without letting them return. It might be a doorway only for light, or only for a probe, or only for a few minutes before the far mouth shifts out of reach. For a lost starship, even that would matter. A voice across impossible distance can be almost as powerful as a road. But a voice is not a rescue. The distinction is gentle and important. A wormhole wide enough for information is not automatically wide enough for matter. A wormhole wide enough for a probe is not automatically wide enough for a ship. A wormhole wide enough for a ship is not automatically safe for a crew. Each step upward in scale adds demands. The route must not only exist, it must remain coherent under the presence of the traveler. In ordinary travel, the road does not care much whether a bicycle or a truck crosses it, as long as the truck is not too heavy. In space-time travel, the traveler has mass and energy, and mass and energy curve space-time. A sufficiently large ship is not just passing through a geometry, it is part of the geometry's accounting. This is one reason the starship point of view is so useful. It reminds us that the passenger is not separate from the physics. Even a fictional vessel of polished hull plates and humming engines becomes, in general relativity, a bundle of energy moving through a curved universe. The ship carries clocks. Every deck has time. The bridge clock, the engineering clock, the tiny oscillations inside every computer, the biological rhythms of the crew, the vibration of atoms in the hull. Near a wormhole or any strong gravitational structure, those clocks may not agree with distant clocks in the simple way they do in calmer space. Time can run differently depending on motion and gravity. For a routine voyage, these differences may be small. For an extreme shortcut, they could become the heart of the problem. Suppose a ship enters one mouth and exits another. How much time has passed for the crew? How much time has passed for the station outside? How much time has passed at the destination? If the two mouths have experienced different histories, if one has moved at high speed or sat deeper in a gravitational field, the shortcut through space may also become a shortcut or detour through time. This is where wormholes become more than transportation puzzles. They become causality puzzles. In a calm bedtime science story, we do not need to chase every paradox. It is enough to feel the shape of the concern. The universe seems to protect cause before effect. Messages arrive after they are sent. Children are born after their parents. A starship that could loop through a wormhole into its own past would not merely shorten a voyage, it would disturb the order that lets events make sense. So the crew asks another question. Does the route preserve sequence? The ship can survive radiation, perhaps. It can reinforce the hull, perhaps. It can launch probes, calculate tides, and wait for the mouth to settle. But if the route breaks causality, the danger is not only physical, it is logical. It is a threat to the story the universe tells about itself. That is why real wormhole theory is so rich. It begins as a shortcut and becomes a test of almost everything: gravity, quantum fields, energy conditions, time, information, and the meaning of connection. The starship before the wormhole is really a starship before all of physics, and the captain wisely still waits. Now let the camera pull away from the ship. The vessel becomes small against the anomaly. The anomaly becomes small against the starfield. Bajor, the station, the traffic lanes, the imagined ships moving in and out of the passage, all shrink into a luminous dot in the galaxy. The Milky Way spreads out, hundreds of billions of stars in a slow spiral. The far side of the wormhole lies across a distance that light itself would need tens of thousands of years to cross by the ordinary route. This is the large scale, the scale of starships and quadrants, of maps and empires, of voyages measured against a galaxy. Quantum foam belongs to the opposite direction, not outward across light years, inward, past the ship, past the hull, past the atoms, past the nucleus, toward the smallest scale where our two great languages of nature may have to become one. To understand quantum foam, imagine the starship again. Its hull is smooth from a distance. From the window of a nearby shuttle, the ship has clean lines, glowing nacelles, dark panels, and the soft reflection of starlight. Move closer, and the surface is not perfectly smooth. There are seams, plates, sensors, ports, tiny textures of material and design. Move closer still, beyond the reach of ordinary sight, and the metal becomes atoms. The atoms become nuclei and electrons. The solid hull becomes mostly space, held together by fields and quantum rules. At each smaller scale, the familiar object changes its character. Quantum foam asks whether space-time might do something similar. From the bridge of a starship, space looks smooth. A vessel can travel through it. A light beam can cross it. Planets orbit through it. Stars move in galaxies. Even the curved space-time around a black hole can be described from the outside with beautiful, smooth equations. General relativity treats space-time as a continuous geometry, a stage that can bend and ripple but remains mathematically smooth. Quantum mechanics teaches a different lesson. At very small scales, fields fluctuate. Particles are not tiny billiard balls with perfectly fixed properties. Empty space is not simply nothing. The quantum world is full of uncertainty, probability, and restless activity. General relativity and quantum mechanics are both extraordinarily successful, but they do not yet form one complete theory of quantum gravity. General relativity is our deep theory of spacetime and gravity. Quantum mechanics is our deep theory of atoms, particles, and fields. But at the smallest scales and in the most extreme conditions, we expect both to matter. We expect space-time itself may need a quantum description. The Planck scale is where this expectation becomes sharp. The Planck length is unimaginably tiny, around 10 to the minus 33 centimeters. That number is so small that ordinary comparison almost fails. An atom is already far below what the eye can see. A nucleus is far smaller than an atom. The Planck length is far smaller again. If an atom were magnified to the size of a solar system, the Planck scale would still be hiding in a depth of smallness that no starship sensor, no microscope, and no ordinary image can simply reveal. This is the scale where physicist John Wheeler suggested space-time might become foamy. Not foam like soap bubbles floating in a sink. Not foam like the edge of a wave on an ocean. Those are made of matter inside space. Space-time foam, if it exists, would be something stranger. Fluctuations in the geometry of space and time themselves, the distances, shapes, and perhaps even the connectedness of space-time might become uncertain. Tiny regions could flicker through different configurations. The smooth map might become restless at its smallest possible scale. The word foam is useful because it suggests a surface that looks calm from far away and complicated up close. But it can also mislead, so we have to hold it carefully. Foam on water has bubbles, it has edges, it has little walls of liquid and pockets of air. Space-time foam would not be a material froth floating somewhere in a cosmic container. There is no outside bucket, there is no background room. The foam, if the idea is right, would be a way of saying that geometry itself may fluctuate when examined at a scale where quantum uncertainty and gravity can no longer be kept apart. Imagine trying to draw a perfect grid on a sheet of glass. At ordinary scale, the grid looks stable. You can measure left and right, forward and back. You can say one point is here and another point is there. Now imagine that as you magnify the grid beyond any human instrument, the lines do not remain perfectly settled. The distances tremble. The angles are no longer absolute. Tiny handles, loops, or changing connections appear in the mathematics and vanish before any ordinary clock could mark them. The image is not literal, but it points in the right direction. The geometry may not be fixed in the way our large-scale minds expect. A starship depends on large-scale smoothness. The navigation computer assumes that a course can be plotted. The inertial dampers assume that the ship has a frame to move through. The communications array assumes that a beam or signal has a path. Even warp drive fiction, with all its invented technology, depends on the idea that space-time can be shaped in a controlled way. Quantum foam is almost the opposite of that confidence. It says that below the smooth stage may be a quantum uncertainty so deep that the stage itself is no longer a simple thing. This is not bad news for the ship. At human and starship scales, space-time appears smooth enough. Planets orbit, light travels, spacecraft navigate, astronauts return home, telescopes focus. The universe does not dissolve under our feet. Quantum foam, if it exists, would be hidden by scale. It would not make the ship rattle as if flying over gravel. It would not turn the bridge floor into a storm. It would be a microscopic or submicroscopic frontier, buried so far beneath ordinary experience that the ship can cross interplanetary space without ever noticing. And still, the idea matters, because every large thing is built on small rules. The calm surface of the sea is still made of molecules. The steady light of a star is still made from nuclear reactions and photons. The smooth path of a planet is still a statement about space-time geometry. If spacetime has a quantum structure, then the grand road of the starship may rest on something stranger than a road. This is where the word wormhole can become misleading. Some pictures of quantum foam imagine tiny wormhole-like connections appearing and vanishing in the microscopic structure of spacetime. But these are not Bajoran wormholes in miniature. They are not little glowing tunnels waiting for tiny ships. They are not a subway system for particles. They are possible fluctuations of geometry at a scale so small and brief that no ordinary object could enter them, steer through them, or use them as a route. A starship cannot fly into quantum foam. The ship is too large by a margin that almost defeats language. Its hull, its crew, its engines, its atoms, even the nuclei inside those atoms are vast compared with the Planck scale. To imagine a starship entering quantum foam is like imagining a continent trying to sail through the texture of a single mathematical point. The scale is wrong. The concept is wrong. The picture must be handled gently. And yet, quantum foam belongs in this journey because it changes the meaning of the question. The Bajoran wormhole asks whether space can contain a passage large enough for a ship. The Einstein-Rosen bridge asks whether the equations of gravity can contain a bridge. Quantum foam asks whether, at the deepest level, space-time itself is smooth at all. That is a different kind of wonder. The starship cannot enter quantum foam, but the starship can help us imagine why the question matters. On the bridge, the crew sees stars as points of light. The navigation computer treats distances as numbers. The helm lays in a course. The ship moves through a universe that seems continuous, but somewhere far below every measurement the ship can make, the smoothness of that universe may be an approximation. Smooth from far away, restless up close, like an ocean seen from orbit, calm and blue, then waves from an aircraft, then foam from a boat, then droplets, molecules, and forces below the surface. The analogy is useful only for a moment. Ocean foam is matter moving through space. Space-time foam would be space and time themselves becoming uncertain. Still, the image helps the mind descend. It gives us a way to feel the difference between the peaceful scale of the ship and the possible turbulence of the smallest geometry. But if quantum foam is so small, how could science test it? This is where the journey becomes very grounded. Science does not need to touch every object directly. Sometimes it tests a thing by asking what consequences it would leave behind. If space-time were foamy in certain ways, light traveling across enormous cosmic distances might be affected. A photon from a distant quasar or gamma-ray source crosses billions of light-years before reaching our telescopes. If tiny uncertainties in space-time accumulated along that journey, the image might blur, or the wavefront might lose coherence, or high-energy light might show subtle signs of traveling through a universe that is not perfectly smooth. NASA has reported tests using observations from Chandra, Fermi, and Veritas, studying light from distant quasars to constrain models of space-time foam. The important result is careful, not dramatic. The observations ruled out some models. They showed that space-time is smoother than those models predicted, down to scales far smaller than a hydrogen nucleus. That does not prove every quantum foam idea wrong. It does something more precise. It tells us that if space-time has foaminess, it cannot behave in certain ways that would have blurred the distant universe more than we observe. The stars and quasars remain sharp enough to teach us. The light arrives with enough order to close some doors in the theory. This is beautiful because it keeps the subject honest. The ship cannot dive into quantum foam, but light has crossed the universe carrying clues. The telescope becomes the starship at another scale. It does not travel through a wormhole. It waits, receives, measures, and asks what kind of space-time allowed the signal to survive. There is a quiet kinship between the bridge crew and the observatory. Both look into darkness. Both trust instruments. Both know that the most important thing is not to force the universe to be more dramatic than it is. In science fiction, the answer often appears on the view screen. The anomaly opens, the ship enters, the music rises, the far side arrives in a burst of light. In real science, the answer may be a missing blur in a quasar image, a constraint, a model ruled out, a scale narrowed, a sentence made more careful than it was before. That can sound small, but it is not small. A ruled-out model is a star removed from a false map. A careful limit is a buoy in the dark. It tells future explorers where not to sail. Picture that observatory as if it were part of the starship's extended senses. The ship has eyes, but not only the eyes on its hull. It inherits every telescope humanity has ever built, every detector buried in a mountain or lifted above the atmosphere, every orbiting instrument that has stared into X-rays, gamma rays, radio waves, infrared light, and the faint afterglow of the early universe. A starship is the child of observatories. Before anyone can fly through the stars in fiction, someone must first learn how to read them in reality. So the ship's science officer studies old light. Not old in a poetic sense only, but physically old. Photons that began their journey before human beings existed, before Earth had its present continents, before countless generations of stars were born and died. These photons cross voids so large that any tiny cumulative disturbance might, in principle, leave a sign. If space-time foam scattered the phase of light strongly enough, distant sources might blur. If different wavelengths accumulated different tiny errors, the universe might look subtly less sharp than it does. This is the same gentle fact that makes astronomy feel like time travel. The moon we see is a moment old. The sun we see is minutes old. Proxima Centauri is years old in our sky. Andromeda is ancient human history and more, arriving as pale light across intergalactic distance. When a telescope studies a far quasar, it is not watching the universe as it is beside us now. It is receiving a preserved message from deep time. If space-time had been foamy enough to disturb that message strongly, the message might arrive softened, blurred, or strangely delayed. The fact that distant objects remain visible and structured becomes evidence. Not the kind of evidence that shouts, but the kind that quietly removes possibilities. The universe is saying, not that model, not that much foaminess, not that kind of accumulated blur. This is one of the most restful forms of knowledge. It does not claim everything. It narrows the dark. And narrowing the dark is what science often does best. The same habit applies to wormholes. We have not seen one, but we can ask what one would do to light. We can ask whether it might lens background stars in a distinctive way. We can ask whether gravitational waves from compact objects might someday show signatures that resemble something other than black holes. We can ask whether the sky contains objects that force us to use wormhole language. So far, it does not. The absence is not a proof that the idea is impossible, but it is part of the honest map. The starship, then, carries two kinds of wonder. One wonder says, imagine the door. The other says, measure the silence where the door has not appeared. Both are needed. Imagination without measurement becomes fantasy that forgets its own boundaries. Measurement without imagination may never ask the question that leads to the next instrument. The fiction and reality path lives between them. It lets a starship approach the wormhole, but it also lets the science officer say gently what the sensors do not show. Now, as our journey turns toward its final movement, there is one more bridge we may mention softly, without letting it take over the night. In modern theoretical physics, there is a conjecture called ER equals EPR. The letters refer to two Einstein-linked ideas, Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement. In certain theoretical settings, especially involving black holes, some physicists have suggested that entangled systems may be related to non-traversable wormhole-like geometry. This is not a communication device. It is not a starship passage. It does not let a crew send a message faster than light or fly through entanglement. It is a deep idea from the frontier of quantum gravity and quantum information, where the meaning of connection may be more subtle than ordinary distance. For our purposes, it is enough to notice the pattern. The word bridge keeps changing. For Deep Space Nine, the bridge is a place ships can cross. For Einstein and Rosen, the bridge is a structure in the mathematics. For traversable wormhole studies, the bridge is a possibility that demands difficult conditions. For quantum foam, the bridge may shrink into fleeting topology, too tiny and uncertain to be a route. For ER equals EPR, the bridge becomes a hint that connection in spacetime and connection in quantum information may not be entirely separate ideas. Each bridge is real in a different way. Fictional reality, mathematical reality, theoretical possibility, speculative texture, frontier conjecture. A calm science journey has to keep those shelves separate. And so we return to the starship. The anomaly still waits on the view screen. Perhaps it is the Bajoran wormhole, bright and stable, opening like a blue-white flower in space. Perhaps it is a less certain distortion, a lensing pattern around something no one has named. Perhaps it is only a region where the ship's instruments remind the crew that space is not empty, nothing, but a physical thing with shape, history, and unanswered depths. The captain asks for the final report. The science officer gives it without drama. The object before them may be safe in fiction, but in real physics, a starship-sized wormhole would require more than a hole in the dark. It would require a stable throat, controlled geometry, survivable tides, ordinary causality, and energy conditions the universe may not permit. The Einstein-Rosen bridge is a clue from general relativity, not a highway. Traversable wormholes are studied but not observed. Quantum foam, if it exists, is not a destination, but a possible whisper of spacetime's smallest structure. The bridge is quiet for a moment, not disappointed, only more precise. There is peace in that precision. Science fiction gives us the courage to imagine a door. Science gives us the patience to ask what a door is made of. Between them, there is a beautiful human habit, to stand at the edge of the unknown and not look away. The starship in our imagination may still enter the wormhole. It may pass through folded light, through a corridor of blue radiance, through a place where the stars become threads and time behaves like a river seen from above. It may emerge in the gamma quadrant, far from home and yet suddenly near. It may carry supplies, questions, warnings, hope. That is the gift of the story. But outside the story, in the real universe, the gift is different. The real universe gives us equations that bend under the weight of stars. It gives us black holes that test the limits of time. It gives us gravitational waves moving through space-time like bells rung by colliding darkness. It gives us distant quasars whose light crosses billions of years and arrives still sharp enough to test whether reality is smoother than some of our boldest guesses. It gives us the Planck scale, not as a place we can visit, but as a reminder that every map has an edge. And it gives us the question, could space ever become a road? For a starship, fiction says yes. For physics, the answer is quieter. Sometimes the mathematics permits a bridge. Sometimes the bridge collapses before anything can cross. Sometimes the bridge requires matter we do not know how to make. Sometimes the bridge is not large at all, but a possible flicker in the smallest structure of space-time. Sometimes the word bridge is not a path through space, but a clue about what space is. That is enough for tonight. Enough to picture the ship holding position in the dark, its engines low, its windows full of bent starlight. Enough to understand that the Bajoran wormhole is a beautiful fictional doorway, and that Einstein-Rosen bridges are beautiful mathematical clues. Enough to know that quantum foam is not another tunnel, not a hidden corridor for vessels, but a possible sign that space-time itself may have a texture beyond ordinary sight. The captain gives no urgent order. There is no need. The stars have waited a long time. The equations have waited too. The unknown is patient. For now, the starship remains at the threshold, not because it is afraid, but because it is listening. Listening to the quiet geometry of the universe. Listening to the old dream of bridges. Listening to the tiny, distant possibility that even space and time may not be smooth forever. And as the bridge lights soften and the ship drifts gently beside the impossible door, the lesson of the night becomes simple. Not every bridge is a road. Not every mystery is large enough to fly through. And not every closed door is empty. Some doors teach us what the walls are made of. The Hypnos Sleep Channel will return with another journey soon, into another place where fiction and reality meet beneath the stars. For tonight, the starship, the wormhole, and the patient foam of space-time are enough.